I'm having a lot of fun as we go through these videos together. The first grouping of videos regarding OSPF was about the concepts and how it works. And then in this section, we're focusing on the actual implementation and verification of OSPF. And we have come to that part of our show where we're going to implement using what we've learned and the hands-on practice we've had in implementing OSPF in a quote-unquote production network. So once again, Bob has called us on the phone and said, hey, I need your help. We need to implement OSPF and verify that it's working. Can you help us? And we say, absolutely yes. Please show us your topology, Bob. We'll set up a plan, and then we'll implement and verify that OSPF is working in the network. So you and I, we sit down in a nice comfortable chair next to Bob, and he breaks out this diagram showing us what their intention is. And so they've got Arizona, Nevada, Florida. They've got Metro Ethernet connecting them together, and they want to implement OSPF. So this Metro Ethernet is simply like a layer 2 VLAN, one network segment, and they're using 10.16.7.0 with a 28-bit mask on that network segment. And router 1, 2, and 3 are all directly connected to it. R1 is using .5, R2 is using .6, and R3 is using .7. And the goal is, with OSPF, is to have full connectivity between any of the networks in Arizona, which are on the 10.16.0/21 block of addresses, and Nevada, which is 10.16.8.0/21, that range of addresses, and Florida, 10.16.16.0/21, and any IP addresses that fall below that. So our mission, should we choose to accept it, is to configure Core 1, Core 2, R1, R2, and R3 to use OSPF. So let's identify where they are. So here's Core 1, here's Core 2, here is Router 1, here is Router 2, here is Router 3. Fantastic. And here are the instructions. Here's what they'd like us to do. Use process ID number 1, so router OSPF. I'll write this out. Router space OSPF space 1. Boom. We press enter. Great. Process ID 1. And all networks are going to be going into area 0. So whenever we do a network statement, we're going to follow it up at the tail end over here with area 0. Fantastic. That doesn't look too bad. They also want us to use 32-bit exact network statements for loopbacks. So that would imply a wildcard mask of 0.0.0.0. So a loopback, for example, on Core 1 or Core 2, whatever it is, we'll do a show IP interface brief, see what that loopback is, and then we'll put in that loopback, all 32 bits, followed by a wildcard mask of all zeros to indicate we want an exact match on that. Okay, that's easy enough. And then this third one says, use /21 network statements for Arizona, Nevada, and Florida networks. Okay, so to confirm what they're talking about here is Arizona has a block of addresses 10.16.00/21. All their IP addresses here fall underneath that block of addresses. And so this is asking us for the Arizona router to use one network statement to include that. And I'm also going to read into that because they want to match on a /21, this guy right here. We want to have it pretty much exact. And for the purposes of this exercise and also for best practice, let's go ahead and give them what they want. So instead of using a really wild wildcard mask, we'll use a wildcard mask that exactly matches for the 10.16.0 network here, and 10.16.8 up here, and 10.16.16 here, all with a 21-bit mask. And then for other networks, if we need to include any of their interfaces and their associated networks, they want us to use network statements with an exact match. So here's what I propose we do for this real-world case study. I would invite you to pause me right now, and pause me and document the network on paper, and then do the lab. And whether you're using Packet Tracer, GNS3, Viral, LiveGear, some other simulator, I would encourage you to walk through every single one of these aspects we have covered in detail in a previous video as part of the OSPF skills. Pause right here and give that a shot on your own, doing that hands-on practice. And then to reinforce the concepts, then go ahead and play me and play me. And then we can continue and compare notes of how we both did it. So that's what I recommend. So go ahead and pause me now. And in a moment, I'll resume and we'll go ahead and walk through the lab solution together. So I've got a question for you. Did you pause me? All right, so let's go to the lab and let's walk through the individual solutions regarding OSPF, both the configuration and the verification that it's working on these Cisco multi-layer switches and routers. All right, so here on our lab machine on DCNUG, our admin computer, we're going to launch MT-PuTTY, and we'll open up consoles to Core 1, Core 2, Router 1, Router 2, and Router 3. All right, so I've got them all open. I've got tabs for Core 1, Core 2, router 1, router 2, and router 3. Great. We can press enter a few times. And let's go into configuration mode. Let's start on core 1. And we'll go into configuration mode, router OSPF 1, and we've got our process ID 1. Boom! That's our first task. It also says use a 32-bit exact network statement for the loopbacks. So we should look at what the loopbacks are. We'll do a do show IP interface brief and press enter. And because it's a multi-layer switch, it's got a whole bunch of interfaces. But the IP address I mentioned right here is this loopback. So it has a loopback with 11.11.11.11. We want to include that in OSPF. So we'll use network 11.11.11.11 space and a wildcard mask that says we have to match on all 32 bits in order for that network to go into OSPF. So we'll do a wildcard mask of 0 bits on, and then we'll add on area 0. Boom. All right, good. So we've done that and that. So now it's asking us to use a 21-bit network statement for Arizona, Nevada, and Florida networks. Now, on a router, we only need to be concerned about, regarding network statements, the directly connected networks that we want to include in OSPF. So here in Arizona, on these Arizona routers, we would want to include the 10.16.0/21, and that would include any directly connected networks that happen to be in that address space. So how do we do a wildcard mask for that network? And let's actually go through that together. So the network we're after is 10.16.0.0/21. Great. And in dotted decimal, that mask is 10.16.0.0 with a mask of 255. That's 8 plus 8 more, 255. That's 16 right there. And we need 17, 18, 19, 20, 21. I'm counting on my fingers. We need 5 more bits. So if we were concerned on what the decimal value is of those 5 more bits from this third octet, we could just write out our table. 1, 2, 4, 8, 16, 32, 64, 128, and we could go for 5 bits. 1, 2, 3, 4, 5. These remaining bits would be off. Our dividing line is right there. And so if we added up all those bits that are on, that'd be 128 plus 64 plus 32 plus 16 plus 8 would be 248. And then for the last octet, it'd be 0. So that's our dotted decimal representation of a /21. Now, you might say, Keith, why are you doing that here? Well, if we're going to do a wildcard mask, we need to flip those bits. So for our network statement, it would look like this. Network, space, and then we'd put our network in 10.16.0.0, space, and then we'd flip all the bits. So you flip all the bits for the 255, you have a 0. You flip all the bits for 255, you have a 0. You flip the corresponding bits, and what you'd have, I'll put this in a different color, is you would have 0, 0, 0, 0, 0, 1, 1, 1. So if we add up all those bits in that third octet, it'd be 4 plus 2 plus 1 more is 7, and that would be our wildcard bits for that third octet, and then the final octet is 0, and we'll flip all those. Now, if you have not seen and gone through the previous videos for both the OSPF concepts and implementing OSPF, we've actually gone through this a couple times with a few examples, so feel free to revisit those videos if you need to. Now, another shortcut for this 7 is you could take 255 minus whatever this dotted decimal mask is, and that also equals 7. So the 255 minus the dotted decimal value is also going to be the wildcard mask for that octet. So that'd be our network statement, space, and then we would add on top of that the area. So area 0. So because the core routers are only in Arizona, that's the only network statement regarding that block of addresses that we need to worry about on those 2 devices. So let's go back to core 1 and let's implement this network statement. So back on core 1, let's go ahead and do a network space. Actually, you know what we should do? Check this out. If we're concerned about did we include the correct network with our network statement, we could do a do show IP OSPF interface brief. Check this out. And it'll show you, yeah, you got the loopback 0. Congratulations. And we can use that same technique again after we add our new network statement for the 10.16 network. So network, based on our plan, 10.16.0.0 with a wildcard mask of I care about the first octet matching, I care about the second octet matching, and I don't care about the first 5 bits of that third octet, which is spelled like this, 7 dot, and I don't care about any of the last octet. And that's the wildcard mask for the 10.16.0.0/21 network. And then we'll add that to area 0. And then we'll do a do. I'll hit the up arrow key a couple times. Do show IP OSPF interface brief. Survey says, got him. So on this multi-layer switch, the VLAN 10 interface, the VLAN 20 interface, the VLAN 30 interface, and the VLAN 40 interface with their respective IP addresses, they all got included. And I think that's it for Core 1. We've got all the interfaces. All the interfaces that have IP addresses, their directly connected networks are now included based on this. We can also type in end. And here's another great command in OSPF. It's show IP protocols. And it's going to show us any dynamic routing protocols that we have running, including OSPF. So show IP protocols, press enter, and look at this. Here's OSPF 1. There's our router ID based on the highest loopback address on this router or on this multi-layer switch when OSPF was started. And it's also showing us the equivalent of our network statements that we added under the OSPF configuration. It's also showing us here what the default administrative distance is regarding routes that are learned via OSPF. All right, that's fantastic. Let's make our way down to Core 2 and do effectively the same thing, except we'll do the network statement based on its loopback address. So we'll take a look at that first here on Core 2. So we'll make a road trip over to Core 2. And on Core 2, we'll do a show IP interface brief. OK, so its loopback is this bad boy right here. I will just click and drag across that to put that in my clipboard. And we'll type in config t, router, OSPF 1, and then we'll add network. Right click to paste in that address. And then the wildcard mask says we care about matching on every 32 bits of that IP address. And then we'll put that network into area 0. Next, we're going to use the same network statement that we did previously. In fact, we can go back and grab it. So if we scroll up a little bit on the previous router, here's our network statement. It was this one right here. So it's going to copy that from Core 1, go down to Core 2, right click, same exact network statement, press enter, and then we'll do an end. And show IP protocols. It's going to show us this information. It's our network statements for OSPF. We have some adjacencies that have formed between Core 2 and Core 1. That's also a good sign. And if we do a show IP OSPF interface brief, that's going to show us each of the interfaces that are involved. And now that we have some neighbors, or a neighbor, we'll do a show IP OSPF neighbor. And because Core 1 came up first, that's why Core 1 is the designated router. If both of these routers had powered on at the same exact time, the one with the highest router ID would have won the negotiation. But since Core 1 already was up and active, there's no preemption in OSPF for the role of designated router on those Ethernet segments. All right, so we've done Core 1, we've done Core 2. Let's go ahead and configure R1 as well. So we make a road trip over to R1, and we'll do a show IP interface brief. And we can also do a show IP route, see what we currently have. And we'll go into configuration mode, router OSPF 1, and we'll add a network statement for the loopback, which is this bad boy right there. And a wildcard mask saying we have to match on all 32 bits, area 0. Great. And then for this network statement regarding the 10.16.0 network, it's the same one we just did on Core 1 and Core 2, so we can just go grab it. I'm going to scroll up a little bit, and in fact, we can just take it right here. This is from the show IP protocols command, but it'll work. So we'll go back to R1 and put in a network statement, space, and right click, and boom, and do show IP OSPF interface brief. All right, and we got gig 20, gig 00, and loopback 0, and we have an adjacency with Core 1. So let's take inventory. We've enabled OSPF on Core 1, Core 2, and Router 1. Let's go to Nevada, or the Nevada router, and let's configure R2 as well. So in Nevada, the big difference is going to be that it's the 10.16.8 network, that block of addresses, that we're going to include in the network statement here on R2. So let's go over to R2. So here on R2, we'll go into configuration mode, and we'll as good practice, we'll verify our interfaces. Do show IP interface brief, and a do show IP route connected. So we're already in configuration mode, but that was a force of habit there. In configuration mode, we'll do a router, OSPF, process ID 1, and let's add our loopback. So we'll type in network, space, and then we can just copy paste our loopback in there, boom, and a wildcard mask of all zeros, and we'll pop that into area 0. Great. Next, let's add a network statement for the 10.16.8 network. And because it's a 21-bit mask, the wildcard mask is going to be 0.0.7.255, just like it was, that part anyway, just like it was in Arizona. We'll put those networks into area 0 as well. And now let's do a do show IP OSPF interface brief. No. Okay, so we have the loopback, which is good, and we have the gig 1/0, but we did not include the other interface. Let's go take a look at our topology. We'll walk through this together. So here on R2, we got the loopback interface, and we also have the gig 1/0, but we didn't get this one. And oh, here's why. This network address space that we're using on the Metro Ethernet between R1, R2, and R3, it's 10.16.7.0/28. That IP address, that network, is not in the range of 10.16.8.0/21. Hence, the router said, well, this interface doesn't match. So thank goodness for this up here. Last statement. For other networks, interfaces, use an exact match. So we'd also want to, here on R2, we'd also want to include a network statement that matches 10.16.7.6 to include it as part of OSPF area 0. And that way R2 can form an adjacency with R1 and start to play the OSPF game with everybody else. So let's add that network statement here on R2. So still in router configuration mode, we'll type in network space 10.16.7. So this is a 28-bit mask. So we need to calculate, for accuracy, we want to calculate what the wildcard bits would be for a 28-bit mask. So let's do that here. And we'll start with the values in an octet of data. And that is 1, 2, 4, 8, 16, 32, 64, 128. If this is a /28, let's put that mask out here. So this part right here, the first 3 octets, 8 plus 8 plus 8 would be 24. And for that last octet, it would be 25, 26, 27, 28. So there's our boundary between network on the left and host on the right. Great. So if we added these up, 128 plus 64 plus 32 plus 16, the mask would be, for that last octet, it would be 240. So what we could do is say, well, if the mask is 255.255.255.240, and we flipped all those for the wildcard mask, it would be 0, 0, 0. And then you could use the trick of 255 minus 240, which is 15. Or we could also do this. We're going to flip all these bits here and just add up the bits that are on for the wildcard mask. So 8 plus 4 more is 12, 13, 14, plus 1 more is 15. Either way, it slices out to 15. So our network statement would be network 10.16.7.0 space, and then 0.0.0.15 for the wildcard mask that is appropriate for a 28-bit network. All right, let me clear my screen. Let's put that in. So the wildcard mask would be 0.0.0.15, and we'll toss that into area 0. All right, now there's a great way right here we can verify that. Well, the fact that we just got a neighbor adjacency with R1 is a good indicator, but we could also do a show IP OSPF interface brief, and that's going to reveal that it just brought in the gig 00 network, which is a beautiful thing. All right, let's type in end, and let's go finish off on R3. So over here on R3, let's take a look at our topology. Here on R3, we want to get the 10.16.16 network in, plus its loopback. Also, we need to include this 10.16.7 network here if we want to have adjacencies and share information across this network interface. So let's go ahead and configure R3. So here on R3, we'll go into configuration mode. We'll do show IP interface brief just to make sure the interfaces are up. Always a good thing. Fantastic. And let's create the router OSPF process. Router OSPF1, boom, now it exists. And then network, and we'll include our loopback right there, boom. And a wildcard mask of all zeros, and toss that into area 0. Fantastic. And then let's get the Metro Ethernet while we're here. In fact, we just did it on R2. We can just copy paste. There's our network statement. That'll include that Metro Ethernet addressing space that we're connected to. So we'll copy that, right click here, boom, that covers that. We should get an adjacency. We do, boom. We have an adjacency with R1 and R2. Fantastic. And next, let's add the 10.16.16 networks with network 10.16.16.0 with a wildcard mask of 0.0.15.255. Same wildcard mask based on the /21 network. And then we'll put that into area 0. Then we'll do a show IP OSPF interface brief. And looks like we got everything. Now, how do we test this? Well, let's have some fun. We've done a lot of work in this real-world case study applying all the OSPF. Let's go to a client. So I've got a client hanging off of here. It's a Windows 10 machine. And this Windows 10 machine is in VLAN 10. And it has the IP address of 10.16.0.10. That's its IP address. The 24-bit mask. And its default gateway is .1. And dot 1 on this 10.16.0.10 network in VLAN 10 is a switched virtual interface address that's up here on core 1. So that SVI is acting as the default gateway on behalf of the clients here. So the traffic, if this client tries to ping, let's go ahead and go down to Florida. Let's say we try to ping 10.16.16.7. That traffic should be forwarded through the switched environment to the SVI, which is at dot 1. It should then route it to R1, who should then route it over to R3, and R3 owns that IP address. That's the predicted path based on how the network is currently set up. So let's try a couple things from that Windows 10 client. We'll do a ping just to verify connectivity out to R3, and if we're brave enough, maybe even a trace route to verify the actual path that's being taken. So in the virtual lab environment, let's go to the client PC. So here on the client PC, I'm going to bring up a command prompt. I would have you do the same thing. Any way you want to bring it up is fine. And let's do an IP config just to verify that we have the IP address we think we do, 10.16.0.10. Default gateway is 10.16.0.1. Fabuloso. Let's go and do a ping out to 10.16.16.7, which is an internal IP address down on the Florida router for their network address space. And we'll press enter. I'll tell you what, I didn't honestly know if that was going to fly. There's a lot of moving parts, but it does. Let's go ahead and do a trace. T-R-A-C-E-R-T, that's how we spell it on a Windows computer, space dash D, as in please don't bother to do name resolution on the way, space, and then we'll put in that same IP address of 10.16.16.7 and press enter, and we'll follow the bouncing ball. And that is beautiful. The first hop was 10.16.0.1, which is a switched virtual interface, a routed interface on the core 1 multi-layer switch. The next hop was .5, which is an IP address owned by router 1. And then that was routed over to router 3, which has an IP address ending in .7. And so I've got a question for you. If we went over to this multi-layer switch, the core 1, and we said show IP route for the 10.16.16 network, what would we expect to see as the next hop from core 1's perspective? What do you think? And if you're looking at the trace output, and you're saying, well, Keith, the next hop was 10.16.6.5, so I would expect to see that as the next hop in the routing table over on core 1. I would agree with you, and I think we should go take a look. Let's go pop over to core 1 and just take a look for that specific route to 10.16.16.0 on core 1. So back here on our admin PC, which is DCNUG, we'll open the tab for core 1, and we can do a show IP route. That'll show us everything. We can page through it. So there's our route right there for the 10.16.16 network. And it was learned via OSPF. OSPF has an administrative distance of 110. The cost to get to that network is 3. And the next hop is via 10.16.6.5, which is an IP address owned by router 1. And this core 1 multilayer switch is using its SVI, switched virtual interface, the switched virtual interface of VLAN 40 as the exit interface, as it forwards that traffic to the next hop of 10.16.6.5. So my question for you is, how did you do? How did you do in the configuration of OSPF? And I'd like to share with you a couple observations that I think might be helpful for many as you start practicing and working with the labs. And that is to use separate devices as you work on them. Case in point, if you have a tablet where you can actually play the video on one screen or one device, you can start it, pause it, start it, pause it, and then on your computer, separate device, go ahead and do the lab. I've also seen people with multiple monitors, and that's okay too. But one thing I've noticed is that they'll pause on the video, and then they'll go to type, but their active monitor is the video. So you have to remember to click back and forth. So if you have two machines, or if you have a tablet you can watch the video on, and then your computer to the labs on, that's going to help expedite it. Once you get that set up and you get a routine going on, videos like this and practical production labs like this are going to be helpful in not only solidifying your knowledge of how OSPF works, how to configure it, how to verify it, it's going to get you better and better at using it. And that way, when you're in a production environment and you have to troubleshoot or implement, you're going to have those skills in your pocket, ready to go. You got this. So thanks for joining me in this video, and I'll see you, my friend, in the very next nugget. Meanwhile, I hope this has been informative for you, and I'd like to thank you for viewing.